In part 4 of module 6, we're going to be looking at the second law for a control volume for open systems. But before we go to part 4, I just want to summarize what we saw in part 3. And what we derived in part 3 is essentially the second law for a control mass or closed system, meaning that the system is closed. Now, for entropy, unlike with our energy and our first law for a closed system, sometimes it's interesting for us to look at entropy from a rate perspective. So we can write the second law as, so for a closed system, we can also write the second law as ds over dt of the control mass is equal to the sum of q dot over t plus s dot gen, which means it's just the same equation but in the rate form. So I just wanted to show you that so that you can apply this to some study problems if you want, but essentially it's the same equation just in rate form and you can apply it to problems. Now, just like we did in the first law, we're now going to consider the most general case, the control volume analysis. And we already looked at closed systems in quite some detail. Now we're going to look at open system, and we'll essentially be adding the contributions from the mass flow rates in and out of the control volume, just like before. So what I'd like to do for this one, and we're going to start with steady systems. So we're going to look at steady systems. So remember, steady systems are systems where the mass flow rate is constant. Then we can draw a diagram that looks like the following. So we're going to look at an analysis of the second law. So we have a system that I'm going to draw, and it's going to be a pretty complex system just because I want to encompass every type of system we could see. So bear with me while I draw this, but essentially we have one inlet on the left and one outlet on the right. So we have mass flow rate in here and mass flow rate out here. And in this system, we also have a piston cylinder that can move up, and we can say that some power is put through this piston cylinder system. And as we said, we have some mass flow rate in, some mass flow rate out. And the mass flow rate out we can also call m dot e for m dot exit. So remember that our convention usually states that we have m dot e. Now, what we also have in this system is we have some potential q dot in. Okay, so we have some q dot coming in. And within the system itself, we also have a change with time of S inside our control volume, and we have some S dot gen that is possibly regenerated. And we're usually going to be using a rate form for the balance of entropy in our systems that are steady, okay? Just like in our first law for open systems, we have a system that is open, and we have a system that uses the rate form. We're going to be using the same thing here for the analysis. So our control volume can essentially be written as the following. So it can be drawn as the following. Okay, it encompasses the whole system, and we have the most, let's say, complex system where we have just Q dot coming in, we have work dot coming out, and we also have some mass crossing the boundary. Okay, and we can start by writing our balance of entropy equation. So the balance of entropy kind of works in the same way as our balance of energy for the first law, but the balance of entropy is going to look like this. So remember, we had written the balance of entropy in words before, so we're going to write it again in the same way. We're going to have the rate of change in entropy. Okay, so the rate of change of entropy is equal to the plus in, the minus out, and the plus generation. And now what we're going to do is we're going to essentially plug in the values that would be in, out, and the generation. So for the ins, we now have some entropy associated with coming in with our entrance and our exit. So we have mass crossing the boundary. When mass crosses the boundary, we have energy coming in, but we also have entropy coming in. So we can say that at the mass in, we, for example, have Pi, we have a certain specific volume I, we have Ti, okay, they're all in. We have energy in, and we also have S in. And at the exit, we have the same thing with sub E, essentially. Okay, so the rate of change is going to be equal to ds of the control volume over dt is equal to the sum of the mass flow rates in, so I, multiplied by SI. So we're going to use I for in and E for exit, minus the sum of M dot E times SE. So essentially, this term is in, this term is out, and then we have another term which has our entropy coming in through the Q dot. So we have this term right here. So this term is usually thought of as in, so we'll leave it as in, but it could be in or out, okay? So this term encompasses both, and you would just use a positive for in and a negative for out. So we have plus sum of Q dot into the control volume over temperature plus S dot gen. Okay, so through this, we've been able to encompass all of our terms. So this is in slash out because you could have positive is in and negative is out. Okay, and we can rewrite this equation as if we have, so this is our most general equation, okay? Now, if we have a steady state system, so our system is steady and we have a steady state system, that means that the change in entropy with time is going to be equal to 0. Okay, the entropy change during the process in a steady process is always going to be 0 with respect to time. Okay, with respect to space, it might not be 0, but with respect to time, it will be 0. Okay, so that means that we can rewrite our equation and simplify our equation to the following. We can say that the sum of the masses exiting times SE minus the sum of the masses in times SI, and remember this is specific, so it's a small s, is equal to the sum of the control volume of Q dot over T, so the Q dot coming into the control volume, plus S dot gen. Just rearranging so that we have our terms separated between masses and heat coming in. And if we have a single flow device, if we simplify the device to have one entrance and one exit, just like we have here in our example above, we can say that Mi is equal to Me. And what that means is that we have M dot Se times minus Si, sorry. Okay, so we have M dot now is exactly the same, so we can just say this is equal to M dot general. So we have M dot Se minus Si is equal to the sum of Q dot over T plus S dot gen. And we can also write this in the following form. So if we divide by M dot, we would have the form SE minus SI, again lowercase, okay, is equal to the sum of Q, little q, over T plus Sgen. And our Sgen would be little s, okay? So this would be this one, and this one would be specific. Okay, so I'll just write specific for everywhere just to make sure that we know that's what we're talking about. And in the above equations, this is not specific on the right. The S dot gen is not specific, but the SE and SI, since they're multiplied by M dot, are specific. Now, if we have an adiabatic system, if the system is fully adiabatic, which means that Q in is equal to 0, there's no mass, there's no heat coming in or no heat coming out, then our actual entropy generation becomes a lot easier. Our equation becomes SE minus SI is equal to Sgen. And then if we want to find the rate of generation, we can multiply by the mass flow rate. Okay, so that's just dividing by the whole mass flow rate and having a few options to use in different types of problems where we're given either Q as a capital or Q as per mass, essentially. Okay, so now that we have an equation for the system, let's try and do an example problem. So we're going to do an example problem from your handout. And this problem is really good because it encompasses a little bit of everything from the first law and the second law, and is pretty comprehensive in trying to understand how to determine the rate of entropy generation and how to use this equation that we just derived. So we have that air in a large building is kept warm by heating it with steam in a heat exchanger, just as shown below. So we have steam coming into our system, and we can see the steam is coming in through entrance 1. Okay, so we're going to use the same convention as in the book. So we have steam coming in at entrance 1, and it exits at entrance 2. Okay, and at the same time, we have air. So we have air at 1 atmosphere pressure enters the unit at 20 degrees and leaves at 30 degrees at about the same pressure. Determine the rate of entropy generation associated with this process. So pretty open-ended problem and a lot of things that we need to figure out, but hopefully it'll make sense once we start analyzing it. So the best way to analyze it is to redraw the system by yourself first, just to understand how the system works and what is happening with the system. So I like to redraw the system in a way that I understand it completely, so that it makes sense to me in terms of what is happening. So I'm going to redraw it. And what I'm going to do is I'm going to have the steam, just like in our previous heat exchanger problem, I'm just going to make it a little bit simpler. I'm going to have the steam running through the middle, and then I'm going to have our air running through the side like this. So I'm just going to have air coming through like this and exiting through the bottom. So we have air coming in through here, and we have the steam coming in through there, just so it makes it easier. And we know that they're exchanging heat, and we know that the steam is warmer than the air. Therefore, we have some Q dot going from the steam to the air. We already know that from our previous examples, and the steam is exiting here and the air is exiting through there. Okay, so I'm going to draw the air in blue just because it's colder, just to show the area with the air. And I'll do the other volume in red, which is the hot side with the steam. And in addition to this is not mandatory, obviously, but I'm going to rewrite what we have. So we're told in the question that we have saturated water vapor enters a unit at 35 degrees at a rate of 10,000 kilograms per hour. So we know the temperature is 35 degrees, and we know the rate is 10,000 kilograms per hour. We're also told that we have saturated vapor. If we have saturated vapor, that means X is equal to 1. Okay, then we're told and leaves a saturated liquid at 32 degrees Celsius. So at the exit, we know that it's 32 degrees Celsius, and we know that X is equal to 0. We also know that the mass flow rate is constant. Okay, so the next thing we can look at is air at 1 atmosphere pressure. So we know we have 1 atmosphere. Enters the unit at 20 degrees. So we have 20 degrees of air and leaves at 30 degrees at the same pressure. So P2 or P, let's call it, this is also 1 atmosphere. Okay, and in our problem, it gives us our numbers for our entrances and exits. So we have the steam is coming in at 0.1, and I'll draw them in green. So I have 0.1 in green. Then I have 0.2 is the exit of the steam, so that's 0.2. And then I have 0.3 is the entrance of the air, and 0.4 is the exit of the air, just to keep the numbers the same as in the problem. Okay, so now we have everything. Now we need to find the rate of entropy generation associated with this process. So how are we going to find the entropy generated? Well, the first thing we're going to do is we're going to write our equation down. The easiest way to do it is to start with our question and write the equation down and figure out what we need to find in terms of our equation in order to solve it. So we're going to write the equation. We know that we have a steady state system here. Okay, we have a steady state system. Our heat exchanger is steady state from both sides. So we can say that our system as a whole, we can take a control volume of the whole system, shown in green, and so we can say the control volume is in green, and steady state means that ds of control volume over dt is equal to 0. The change in s with time is going to be equal to 0. There's no change in time. Now, what we can do is we can write our equation. So we can either start from the very first equation, or we can go to our simplified steady state equation already. So we can say that the sum of the masses flow rates exiting times SE minus the sum of the mass flow rates in times SI are equal to the sum of Q dot over T plus S dot gen. Okay, so we have our equation written down. And now we can plug into our values. But before we plug in, is there anything we can cancel? So if we look at the question again, we're going to make another assumption. We're going to say that the system is isolated. Okay, so we're going to assume that the system is completely isolated. So we're going to say that the heat exchange out of the system or into the system from the outside, this heat exchange here, there could be a Q dot coming in. We're going to assume that this is equal to 0. Okay, we're going to make that assumption because we don't have any information on that. So since this is 0 and we're using the whole control volume, we can say that the Q dot coming into our system from the outside or from the surroundings is going to be equal to 0. So we can cancel this and say it's equal to 0. The change between the two systems is not equal to 0. So Q dot between the two systems is not equal to 0. However, in this case, we're going to assume that we have an adiabatic process with the outside. Okay, we're going to assume that it's insulated from surroundings. So this is going to be the assumption, insulated from surroundings. And if it's insulated from surroundings, it goes to 0, and therefore we can rewrite our equation as follows. So we're going to do the sum of all the mass flow rates exiting times SE. So we're going to say mass flow rate of water. Okay, I'm going to call it water just because it's steam on one side and liquid water on the other side. So I'm going to call it mass of water times SE. So it's ME of water times SE of water, W, plus M dot air, which I'll use an A for air. Okay, that's again exiting. So I'll have mass E of air exiting multiplied by SE of air. Okay, and I'll just put A for air, not the whole word, just to stay consistent, minus M dot I of water times SI of water minus M dot I of air times SI of air. Okay, and that's all equal to S dot gen. Now we know that M dot I for each respective system is equal to M dot E. So we can rewrite all of our values. We can get rid of the sub E in the mass system. Okay, so we can just say M dot W, M dot A, etc., etc., and for all four terms in the equation. So we can simplify this equation and rewrite it as S dot gen is equal to M dot of water times SE minus SI, all of water, plus M dot of air times SE minus SI of air. Okay, and remember those are lowercase s's. And now what we have to do is we have to figure out from our system, we have to figure out our terms for, so we have to figure out our mass flow rate, our SC, our SI for water, our SC, our SI for air, and our mass flow rate for air. Okay, we already have our mass flow rate for steam. Do we have our mass flow rate for air? No, we don't. We don't have that mass flow rate yet. So we're going to be able to find it through our first law analysis. But first, let's try and find our values for SE and SI. Okay, so what we're going to do is we're going to use two different techniques. So first, we're going to look at for water. So we can say for water, we have to find SE minus SI. So what technique are we going to use to find SE minus SI? Well, we know we have water, and if you have water, you go to tables. So we're going to use our tables in order to find SE and SI. So our water at the entrance has two properties given to us. We have that the temperature I is equal to 35 degrees Celsius, and we know that the quality is equal to 1. And then we know that the temperature at the exit is equal to 32 degrees Celsius, and we know that X is equal to 0. So from this, we're going to be able to use our tables to find SI and SE. So let's go to our tables and find them. So if we go to our tables, we can go to table A4 for water, with the temperature. And in our tables for temperature, we're going to go to the temperature that's required. So we can say that our first temperature is 35 degrees. So we know that our system is at 35 degrees. We also know that we are at VG essentially. Okay, so if we needed VG, we could find VG from here. We can also find UG, HG, and we can see in the last column we have SG. So we can get SG from here. So SG is going to be equal to, and remember that X is equal to 1 is at SG. So we have that this is equal to 8.3517. So going back to our OneNote, we can write that SI is equal to 8.35117 kilojoules per kilogram Kelvin. Okay, we have the units up there, so we can write the units down. And then and I meant SI for that, okay? So the next thing we're trying to find is at the exit. So at the exit, we have TE is equal to 32 degrees. So we're going to have to interpolate between these two values here. So we're going to have to interpolate for SF, because now X is equal to 0. We're going to have to interpolate between this value and this value. And if you interpolate correctly, you should get 0.4641. So our S at the exit is going to be equal to 0.4641 kilojoules per kilogram Kelvin. Okay, so we can say that from this, we've been able to get, we will be able to get SE minus SI. Now, what about for air? For air, we have to make an assumption. We have to assume ideal gas so that we can use our equations that we developed for ideal gas. And the equation that we developed for ideal gas is SE minus SI, and we'll use the small lowercase, okay? We'll use a specific equation, so this is specific. So without the mass flow rate, or without the mass, sorry, we'll get that SE minus SI is equal to CP average times ln of TE over TI. And we also know that we have this term, and this term is usually minus R ln of P2 over P1, or PE over PI. Now, what does that mean? Does this go away? Well, this second term is going to go away. The second term is going to go away because pressure at the exit and pressure at the entrance are going to be the same. So we can get rid of that second term. Makes it very easy. Then what we can do is we can apply to this equation, we have to find CP average. Our CP average, once we find it, is 1.005. So we can do 1.005 times ln of TE over TI. We have the exit temperature, we have the entrance temperature. We convert them to Kelvin, and we get that SE minus SI is actually equal to 0.0337. Now, for this system, we could have used another equation if we wanted to as well. We could have used a special case equation. Because we're using the CP term, we could have said that SE minus SI is equal to SE0 minus SI0 minus R ln PE over PI. Again, this term would go to 0, and we would be left with SE0 over SI. And so we could have gone to our tables and found SE0 and SI, so I'll show you in table A17. You can use this method as well. And in table A17, you have your S0 values, where you can find your values at different temperatures. So if you convert your temperatures to Kelvin, you can then go here and find your values for S0, and you would then interpolate, obviously, because you're going to be between two different values, and you could have found your S0 for the two different temperatures and subtracted them from each other. Now, it's up to you if you want to use S0 or CP average. Usually, it's faster to use CP average just because you don't have to interpolate. However, if you don't have to interpolate and you have the temperatures already in Kelvin, for example, you have 300 Kelvin minus 290 Kelvin, then it might make sense to use S0. Okay, so in this problem, I specifically used CP average because it was very easy. It was just CP at 25 degrees Celsius. However, you can also use SE0 minus SI0. So it's up to you to choose one or the other. Now, you can only use the S0 equation for the equation with ln of P2 over P1. You're not allowed to use it for the CV average equation with the plus R ln of V2 over V1 because it's not for CV. The S0 is to work with variable specific heats that are associated with CP, not CV. Okay, just an extra bit of information here. So you could have used this second equation if you wanted to, and you can actually practice this to see what you would get in terms of your values. So this would be kilojoules per kilogram Kelvin. Now, moving forward from this, I want to iterate something else that we haven't really looked at yet. When we look at ideal gas equation, if needed, you can also say that the ideal gas equation, when written in rate form, would be equal to PV dot is equal to M dot times RT. So it's the volume flow rate is equal to the mass flow rate times RT. Okay, that might come in useful sometimes in these kinds of problems. Okay, so now we have SE minus SI for both systems. Okay, so, and we have the mass flow rate of water. Let's write down the mass flow rate of water so that we have it. The mass flow rate of water is 10,000 kilograms per hour, which converts to, in seconds, to 2.78 kilograms per second. Okay, a lot easier to follow if it's in kilograms per second because that's the units that we're going to use. So mass flow rate of water. Now, how are we going to find our last term, which is the mass flow rate of air? So to find the mass flow rate of air, we're going to have to do a first law analysis. And we're going to have to use our whole analysis of what we've done before for our heat exchangers. So how did we solve heat exchanger problems? We looked at the water side and we defined our first law for the water side, and then we had to look at our first law for the air side. So we're going to look at our water side to find Q dot essentially, and then from Q dot we're going to be able to find the mass flow rate of the air. We've done similar problems before, so I'm not going to go into a lot of detail on how to do this, but you can definitely do it into detail if you want to. So how it's going to work is we're going to write the first law and we're going to do the water side first. So we're going to take a control volume from the water side. And we know from our water side that we have Q dot minus work dot is equal to delta H plus delta PE plus delta KE. And we don't have any potential energy change or any kinetic energy change. We're not given any changes in velocity or height, so we can get rid of those terms. And we're left with Q dot in, and we also don't have any power. We don't have any moving parts. So we're left with Q dot in is equal to M dot water times HE minus HI. And for our exit and inlet, we can find from tables, we can find HE and HI. So remember from our tables, we've already found SE and SI. HE and HI are found in exactly the same way. So I'm not going to go over this again because you know how to do this and you should have practiced this already in a previous module. So now we can say that Q dot in is equal to 2.78 times the values of HE minus HI. And the values of HE minus HI are written in the equation here. So you should get 134.10 minus 2564.6, and that would be equal to negative 6,751 kilowatts. And that makes sense. We have a Q dot into our system that is negative. It makes sense. We actually have some energy coming out every second. So it makes sense that the value was negative. So we can also write that Q dot out, which is the opposite, would be equal to 6,751, which confirms that the direction of the Q dot is from the hot water to the cold water, just like we drew in our initial stage right here. Okay? So now that we have this, we now have a Q dot, and we can use this Q dot for the air side. So now we're going to look at the control volume for the air side. Okay, we're going to look at control volume analysis of the air side. And for the air side, we essentially have the exact same equation. Q dot in is equal to m dot HE minus HI for the air. And since air is an ideal gas and we have the temperatures at the exit and the entrance, we can use our CP once again, or we could use our tables to find our H's. Okay, it's up to us. But we know that the Q dot in for air is going to be equal to the Q dot out for water. So we have that this is 6751 is equal to m dot of air multiplied by CP 1.005 times TE minus TI. Okay, our T minus TI is 30 degrees minus 20 degrees. So we can just plug those in. And we finally get a mass flow rate of air, which is equal to 671.7 kilograms per second. The reason I use CP times temperature change is because the temperature was given in Celsius, and in our tables it's in Kelvin, so I would have to convert temperatures to find HE and HI from our tables. So in this case, it's actually faster to find CP times delta T than to use a table A17. So the alternative would be to use table A17, but you would have to interpolate in this case. And since you're given the choice to use one or the other, then in this case, it makes sense to use CP average. Okay, remember, it's always average. And now that we have the mass flow rate of air, we have all the terms for our S dot gen. So we can say that our S dot gen is equal to the mass flow rate of water times SE minus SI. We have those values, plus the mass flow rate of air times SE minus SI. We also have those values, and we just plug in all the values, and we get that our entropy generated per second is equal to 0.745 kilowatts per Kelvin. Okay, so SGen capitalized is just kilojoules per Kelvin, and in this case it's kilowatts per Kelvin because we're looking at the rate. Okay, so it makes it very simple to use. Okay, now let's look at the next thing that we want to go through, and the next real subject that we want to go through is the following. We want to look at steady state single flow process. So what happens when we have a steady state single flow process. So before we sort of had a more general approach to the problem where we have a process that can be steady state but has multiple flows. Now we're going to derive an expression for the work output in a single flow steady state process. So we're going to derive an expression for work output. Okay, so we're going to look at work output. And what we can start with is the first law and the second law. So let's write the first law and second law for a steady state process in general. So we can say the first law, and we're going to write it in a little bit of a different way than we usually do, but it's pretty much the same thing. We're going to have all of our in terms on the left side and all of our out terms on the right side. Okay, so instead of having Q minus W is equal to HE minus HI, we're going to bring all the HIs to the left, all the things coming into the left, and all the things coming out to the right. So, and we're also going to write it in specific form. So we can write that QI plus HI plus 1/2 VI squared plus GZI in the most general form is equal to HE plus 1/2 VE squared plus GZE plus work E, or work out. Okay, and we're actually going to drop the E here on the right, and we're going to drop the E on the Q because we usually assume that work is out and Q is in. Okay, we know this assumption from previous. So this is going to be called equation 1. Okay, so you can refer back to it. Our second law analysis now yields the following equation. We have that SI plus Sgen, and again, all lowercase, plus dq over t, so the integral of dq over t, is equal to SE. Again, in is equal to out. Okay, we're writing it in form of in is equal to out. Okay, we can also write it in differential form. So if we want to write it in differential form, we can bring the SI over to the right, and we would have ds gen plus dq over t is equal to ds, okay, which is the change in SE minus SI. Okay, and we also know that we had derived earlier that dq in the previous part, dq is equal to TDS, sorry, this is a lowercase s, minus TD Sgen. Okay, so we remember those two equations, and we're going to call this equation 2. Okay, and we also know from our properties and from the Gibbs equation, essentially, so our property equation or relation says that TDS is equal to DH minus V dP. We're going to call this equation 3. Now, let's substitute 3 into 2. So let's make the decision of substituting equation 3 into 2. So we're going to plug in TDS into 2, and we're going to get that dq, okay, so we're going to substitute this one right here. We're going to say that dq is equal to dH minus VdP minus T ds gen. Okay, just by plugging in for our TDS. And now if we integrate the whole equation, we have the following integral. We have Q is equal from inlet to exit of a single flow device, okay, so dq is equal to the integral from in to exit of dh minus vdp minus t ds gen. Okay, so bear with me while we go through this derivation because something good will come out of it. Okay, so we now integrate this and we get that Q is equal to HE minus HI. Okay, so if we integrate this side here, we get HE minus HI minus the integral from I to E of V dP minus the integral from I to E of TDS gen. And we're going to call this equation 4. Now, what we're going to do is we're going to substitute equation 4 into our first law. So if we do that, we're going to substitute for our Q on the left side. So we're going to have HE minus HI minus the integral from I to E of V dP minus the integral of I to E of T ds gen plus HI plus 1/2 VI. Let me rewrite that. So VI squared plus GZI is equal to HE plus 1/2 VE squared plus GZE plus the work out. And now we can come up with an expression for our work. Now, before we get through an expression for our work, let's cancel out some values. So we see that we can cancel out HE and HE on both sides. So HE is going to cancel from both sides. And we can also cancel HI from both sides. So we get rid of the HI term. And since the heat has been translated or changed to a term between H, VDP, and TDS gen, we can now solve for the work without our heat term. So we can solve for the work of our system to say that the work is equal to minus the integral from I to E of VDP plus 1/2 VI minus VE, both squared, plus G ZI minus ZE minus the integral from I to E of T ds gen. Okay, and remember that this work here, this equation for work, is per mass or specific. Okay, so you would have to multiply by the mass flow rate to get the power, or by mass to get the work. Okay, so for turbines, pumps, and compressors, we can simplify our system a lot. So if we have turbines, pumps, and compressors, we usually know that delta KE and delta PE for pumps, turbines, and compressors, those are the things we're usually interested in thermodynamics. We can say that our shaft work is now given by the following area. So the shaft work for our system is going to be equal to work, which this is what we call shaft work, because it's the work from a pump, turbine, or compressor usually. And this work is just going to be equal to minus integral from I to E of V dP. And we get rid of all the other terms, including the TDS gen term, because usually our entropy generated is very, very small through that system. Okay, so the entropy generated in the system is so small that we usually don't take it, we don't add it to that equation. So our shaft work can be said to be work is just equal to the minus integral of VdP. And you could be asked to find the shaft work of something in this class as well, but this is more of a derivation to understand how it works. Now, if the fluid is incompressible, so if we assume the fluid is incompressible, then we can write our equation if we don't take out the pressure, if we don't take out, the velocity and height terms, we have that the work is equal to minus V, which is specific volume, times PE minus PI. Okay, now that we have we can integrate it because we have no change in pressure in our fluid, plus 1/2 VI squared minus VE squared. And I meant to say no change in specific volume in our fluid, not change in pressure. So the change in specific volume is insignificant, so we can take it out of the integral and then integrate the pressure, plus G Zi minus Ze. And you'll notice that this is equal to the Bernoulli equation. So this is equivalent to Bernoulli equation that you might have seen in a transport phenomena class. And if you haven't, you'll see it in physics or transport phenomena. So we can essentially say that VPI would be equal, VPI plus 1/2 VI squared plus GZI would be equal to a constant. Okay, would be equal to the term at the other. And remember that V is equal to 1 over density. So you might have seen it in a different way where it is 1 over density. Okay, so we have that our Bernoulli equation is essentially called, this first term is called our flow work. This is KE and PE. Okay. Okay, so moving from this, we're going to be looking at efficiency in the next part of Module 6, and this will be our last part for Module 6 and our last part for the class. So see you in the next part where we're going to talk about efficiency and do a lot of examples on the efficiency of compressors, turbines, and pumps as well.